Okay, so if you're in a state where you have a failed suspend resume sequence, as we have here, we're going to want to do some debug to determine exactly which power domain wasn't able to transition. So we need to do that by connecting with JTAG when we are almost in the deep sleep 0 state. So to do that, I've built a couple different versions of the firmware. You can see I'm using a symlink for the firmware file itself. So currently we're using the .new, which was just the version that shipped with Processor SDK 2.0 plus a couple other patches. And I have another version of that same firmware that I added a spin loop at the end of the Deep Sleep 0 handler, and that's the .spin. So I'm going to go ahead and change this to point to a different file so I can get the firmware with the spin loop. All right, let's double check that. Okay. Looks good. So now I'm going to reboot, and when it boots, that will load the new firmware. Okay, so I'm back up. Again, we're simulating a bad driver here. So what I have, let me take my timer 7 and enable that clock again. There we go. Okay, so now we're in the state where the suspend resume is going to fail. And I now have my firmware with the spin loop loaded. So let's go ahead and let's attempt to suspend. All right, so now we should be spinning in a while loop in the Cortex M3 handler. So let's go ahead and take a look at things. So under my target configurations, I've specified the JTAG that I'm using, and I've also selected the AM335x as a device. I can go ahead and launch that configuration, and once that's launched, now I want to open up the scripting console, and I'm going to load a debug server script to help me debug the issue. So I'm going to go ahead and use load.js file, pass it the path of my script, and now it's going to go ahead and interrogate a bunch of the registers, and you can see it's now created the file that it mentioned there. Let's go ahead and take a look at that. So if we open up this file, now we can see that the Cortex A8 was powered off, the graphics was powered off. However, the per domain is on, and furthermore, it's looked at some of the registers in the per domain, and it's able to tell us that timer 7 is active. So this is how you would narrow down what specifically is causing an issue. One other related tool that you may want to use is there's another script specifically for getting a dump of all the clock tree registers. So since we've got the target halted in this perfect spot for capturing data, let's go ahead and run that one as well. This one is going to give us a .rd1 file as the output, and we can open this one. This one just has a whole bunch of registers and the corresponding address. So for example, you can actually see in here, you can actually see the register that we modified. Here's the timer 7 register that we enabled. This can be useful to compare between a known good and a known bad because it has all the clock data captured in this, and this can also be imported into the clock tree tool. So this is very useful for being able to determine which clocks might be causing an issue. So finally, now that we've determined our clock, we want to be able to wake back up. We do that by connecting to this wake up M3 subsystem. Sometimes you may have to do show all cores to see everything. In this case, seems to be there. So we're going to go ahead and connect to that. And now we're connected. I open a memory browser. If you type in SP for the stack pointer, this second item on the stack is actually the variable I set to spin. So instead of 1, we want to set this to 0 so that the M3 will complete going to sleep. And if we simply disconnect from the target, that'll set the M3 running again, and it will complete going to sleep. So if I go ahead and do that, now it's disconnected and running, and we're now asleep. And now I can hit the key and wake us back up. And now we're able to go and fix whatever issue we might have. In this case, it was a issue we created ourselves, but normally this would be where you'd go start debugging a driver.